Okay, so it's time to start now. And first I just want to let you know that I've decided from now on we are going to have homework due every Tuesdays and Thursdays instead of Mondays and Wednesdays. And office hours are a little more consistent. Monday, Tuesday, and Wednesday, they're going to always be the same time. And then Thursday, it's earlier, just because there's a seminar in the late afternoon that people have to go to. So, but if you can't make any of those times, just send me an email. All right, now let's move to the document camera. And we have a little more to do in this, in chapter 9. We just have this last page, and this is what you have homework on tonight for those of you who haven't tried it yet. So let's remember what we were doing here. We have we're just looking at figuring out the expected values and the standard errors for sums, averages, percents when we know what's inside the box. And then we're drawing these we're drawing these histograms for the distribution of the samples we get. All right, so here is our box right now. And this box has an average equal to 3 and a standard deviation also equal to 3. So if you want to figure out, you take 36 draws from this box, right here, 36, and it's with replacement. And then what would you expect the sum of the 36 draws to be? Well, you could get all zeros theoretically or all 8s, but you'd expect on the average to just have n times the average of the box. So the expected value of the sum is equal to n times the average of that box. So that's just 36 times 3, which is 108. So that's what you'd expect for the sum. And then but it's not going to be that every time, of course, it varies. And how it varies is called the sampling error or the standard error. And the way I always tell you to remember it is to say, okay, a standard error for anything, here we're doing the sum of the draws, we could do the average, but it's like a standard deviation for a chance process. So just write standard deviation. But it depends on how many draws you take, right? So for the sum, we're summing up our errors. So it's either times the square root of n or divided by the square root of n. But for sums, it's times the square root of n. So it's just going to be 3, the standard deviation, times the square root of 36. So that's 18 here. So that's pretty simple. And so now we want to answer this question: what's the probability that the sum of those 36 draws is going to be greater than 120? So we know that the probability distribution of the sample sum, average and percent, is going to follow the normal curve as long as the number of draws is big enough, and that's pretty big. So we're going to use the normal approximation here. So we just have to match up what we get. This is our z, in terms of z-scores. We're just going to match up the sums to the z-score by using this formula. Z is going to be equal to our value minus our expected value over the standard error. Remember, for a list of numbers, it's just the value minus the average over the standard deviation, but now we're looking at these random variables. So, and here we're talking about sums. So that's what we have. So just to remind you, the expected value is going to be right in the middle. That's 108. And we're asking for, here's our value, 120, where to place 120 on here. Well, we know, so our value is 120 minus the expected of 108. So we know that's 12 above, but what is it in terms of these standard errors? Well, each standard error is 18. So 120 is just 2/3 of the way over towards the next towards the standard deviation. It's a z-score of 0.67, 2/3. So between 0.67 and negative 0.67, .67 is a z-score, matches up with 120. Okay? Does that make sense to everybody? And what area do we want? We want greater than 120. So that's why we're getting this. We have to find, the table will give us this middle area. So if you look up on the table, the middle area, 0.67, well, it's between 0.65 and 0.7, so I just estimate it as 50%. Okay, does that sound good? It's between 48 and, just to make it easy here in the class, and we can all do this together. So that's 50% of the area right there. And we just want that part. So if that's 50%, the two tails together have to be 50%. So this one's 25. That one's 25 too. So our answer is 25%. That's the probability. Any questions? Yes? Yeah, express it as a percent here. Because usually when we're looking at areas under the normal curve, we express it as percents. All right, now, what if I'm not interested in here's the sum, but now I'm interested in the average, okay? So these were the sums. So the average is even easier. You know, you'd expect the average of your draws to just be the average of the box, right? So this is really just simple. It's just 3. But what is the standard error of the average? Well, here you have to think, okay, the standard error of our sample average, it's like an SD, but now the average, instead of take an average, you divide by n. So if we divided that by n, we wind up with SD divided by the square root of n. Remember, for all these standard error formulas, you either multiply by the square root of n, you do for the sum, or else you divide by the square root of n. And that's what you do for averages and percents. So here it's just 3 over the square root of 36, which is just a half. So now, once we know those two facts, and we know that the sampling distribution follows the normal curve, that even though, because the box is not so lopsided, and it's not going to take very long for it to follow the normal curve. So in 36 draws, that's enough. We can do the same thing. So here, 0, 1, 2, 3, negative 1, negative 2, and negative 3. But now our value is 4, and we're talking about averages. So we're using the same thing, value minus expected, value over standard error. That's what we're always using, but this time it's for the average. So now we can see our value is 4. We'd expect what? 3. Let me just show you down here. Okay, so here is the average. We said we'd expect, that's where the expected value is. We said we'd expect 3. You can see this one real easily. The standard error is 0.5. So here's 3.5. And here's where 4 would be. That would be 4.5. And that's, so we're going to get, it's 2 standard errors. And you can see that we're 1 above. But in terms of how many standard errors that is 2. Okay? So we want less than that all the way down. So between 2 and negative 2, let's just approximate it with 95%. That's that 1, 2, 3 rule. So now we know each tail is 2.5%, and we want all the area below. All of this plus that tail. So that's just going to be, so our area is going to be 95% plus 2.5%. everything but that tail. Okay, it's this plus all of that. Any questions on that? All right, so let's just do the one last one, and then this sort of sums it up. And you have a, unfortunately, I think the problem that I put on your homework is almost identical to this, if not identical, right? Very similar. Might be randomized. I hope it is for you guys. But for some people, it's identical. All right. So now let's say we're interested in percents of something. Well, percents are used when you classify something as either the percent of 2's. So either it is a 2, yes, or it's not a 2, no. So the expected value of the percent of 2's in this box is just going to be the same as the percent in the box. What we'd expect in our sample is the same as what we know in our box. So that's just going to be, there's 50% 2's here. So just like this, so it's the same. For percent in average, the expected value of your sample percent is just going to be the same as the percent in the box. So there's really nothing you have to do there. But now for the standard error of the percent, how are we going to figure that out? Well, we can't use our old standard deviation. We have to change this. We're just counting whether something's a 2 or not. So we're going to change this to a box that's just 0's and 1's. So what would be the box? Well, if you get a 2, you count it as 1, 2. But if you get anything else, you're going to count it as 0 2's. So that's your new box, and it's just 50% 1's and 50% 0's. 50%, but what's the standard error? Well, remember what the standard error for the percent is. The standard error for percent, again, standard error is standard deviation, right? Now, percent, you divide by the square root of n. It's really, percent is just an average, really. It's like the standard error of the average for a box that just has 0's and 1's. If you did it this way, you'd get percent as a decimal. But we want to do it in terms of percent, so we just multiply by 100 to turn it into a percent. But it's really, these two formulas are the same. It's just, this would give you, this is a special case of that. All right, so let's just do that. So we need the standard deviation of this box. You should know it. It's a 50-50 box. So it's just the square root of 0.5 times 0.5, which is 0.5. So that's our standard deviation. So then our standard error for percent is going to be 0.5 divided by the square root of 36 times 100. And that is 8.33%. So that's what we got so far. And now we just want to, here's our value right here, more than, we want the probability that the percent of 2's is more than 60, right? So we have, again, here, let me just draw this again. And here is a percent, what do we have? Our expected value is 50, and our standard error is 8.33%. So if we went up to 58.3, if we add it, it's 8.33% up to 58.33, that would be 1 standard error, or more than that. So what is it? It's Z is going to be equal to, again, sorry to write this so many times, but you'll remember it if I do. Okay, so now we have 60% minus 50% over 8.33%. The percents all cancel out, right? And we get 1.2 as our z-score. So that's where 60% lies. We knew it was above 1. There it is. 60% is right there. And that's a z-score of 1.2. So between 1.2 and negative 1.2, we can look on the normal curve, and it's 77%. You can check that out. And so what do we want? Just be a little careful here. More than 60. So it's just that percentage, just that tail. So these two together are 23. So each one of these would have to be 23 divided by 2%. So our answer is 23 divided by 2%, which is 11.5%. So, any questions on any of that? Okay. Now, we're going to skip this. Unfortunately, we just don't have time. So skip, and maybe someday we'll come back to it. But for now, you don't even have to do it on your own, because we don't have time. And of course, every summary, read. I can't stress that enough. Read them carefully. Now, we're going to go on to chapter 10, because I want to cover 10 and most of 11 today. So you can do the homework that's due Thursday. So, now, what have we been doing so far? We've been looking at standard errors and expected values for games of chance, or games or situations where we know the box. We know what's inside the box. All right? And they translate very easily into box models. But now we're going to look at surveys, survey data, where we generally just see one survey sample, just one sample. We don't know what's in the box, the population, and we're trying to estimate that. All right? So obviously we take a sample because we don't know what's in the larger population. We don't know what's in that box. And so obviously, the closer this sample resembles the population, the better our inferences about the population parameters will be. Remember this terminology here. Population is, in our examples, the population was the box. It's like what we're taking samples from. But now we're going to be looking at like political surveys, political polls, things where we take a sample from a much bigger population, and we're going to make an inference from the sample to the population. So, remember, parameters are the numerical facts about the population we're trying to estimate with our sample statistics. So that's the idea, and this, of course, is the main idea. How do you make the sample as representative of the population as possible? And I think that after our discussion of how it is very similar to how to make a treatment and control group as alike as possible. And in the early days of political polling, they made a lot of mistakes by not making by introducing bias, by using too much, humans tried to make, they did this all the time, quota sampling. The researcher handpicks the sample to resemble the population on all the relevant characteristics. That seems great to do, but it's good as a first step only because, as we saw before with in our experimental design, trying to match the treatment and control group, that you want the final step to include a randomization process. Should be random assignment, some kind of randomization process. Okay? Otherwise, bias is introduced. If humans, they might, for one thing, they don't identify all the relevant characteristics, and they might introduce a lot of systematic error in deciding who among particular demographic groups they're going to choose. So otherwise, bias is introduced. We saw that before. All right. Now these are very popular. They used to be these self-selected samples because they're very easy to do. And you simply post on the web or post on TV or somewhere, say, hey, call such and such a number to vote, or go to such and such a website. And these have huge selection bias because people are selecting themselves, and those who feel most strongly about an issue are going to be overrepresented. You know, who would go to a site to ban weapons, ban guns, or who would go to a site to ban abortion or whatever, and to vote for the people who feel very strongly about the issue. Okay, so it's huge bias. Selection bias, those who feel most strongly are most likely to vote. So you won't get a representative sample. Your survey results are not going to be reflective of the population as a whole, if that's what you're trying to do. It'll just be representative of a population who are very eager to respond and who go to that website. So these are biased, so they're not very good. These are biased samples, so they're not good. And the probability sample's the best. That's a random sample, randomly selected. Okay? And this is the best. And why is it the best? Because random sampling, where everyone has an equal chance, one way to do it would everybody in the population has an equal chance of being chosen. That would be the simplest probability model. It eliminates selection bias. Okay, but there's other types of bias that remain that have become a real problem for polling, because it used to be that people would answer their phone. Now they don't. So we'll discuss those in a minute. Did you have a question?
Well, like, if you do it randomly, isn't it still like people that care are more likely to respond?
That's a different type of bias, though. Selection is just who's selected. Now, what she's talking about is there other types of bias, because everyone knows you get called up for a survey, and then a lot of people are not going to respond. That wouldn't be such a problem, except what she's saying is that the people who do respond are systematically different than the people who don't. Probably people who face the same issue, people who feel the most strongly about the issue. So let's look at that. That's right here. Probability methods eliminate selection bias, but there's still other possible sources of bias. And this one that she just mentioned is extremely important. And then there's another one too we'll talk about. But first, let's go to the top of the page and remember how that random samples are best for surveys for exactly the same two reasons that randomized controls are best for experiments. And that's why we can sort of go through this very quickly, because we already went through it with randomized experiments. Remember what our goal is. This is our goal for randomized experiments was to have the treatment and control group as much alike as possible. Here, our goal is to have the sample and the population as much alike as possible. And we saw that blind chance works better than human judgment. It's less likely to introduce bias, okay? Random selection is most likely to make them as alike as possible because it eliminates selection bias. All right, and then we know with enough subjects, those random differences average out. And here's what's important too, not only on the characteristics that we know are important, but on all characteristics, including hidden ones that the researcher might not have realized were important. So that's one reason. And the second reason is because it allows us to use our standard error formulas. It allows us to use the statistics we know, to use probability, to model this. If we have a random selection process, then we can use probability models. The one we've seen is the box model. And from that, we can calculate standard errors the likelihood of the chance error. So without a chance process, we really couldn't use statistics to analyze the accuracy of the survey. So what it does is it allows us to calculate expected values and standard errors and sampling distributions. All right, so now let's go down to, even though we eliminate the selection bias, that doesn't mean we're finished. In fact, polling right now is very complicated because of this huge non-response bias, okay? Random selection eliminates bias in who is chosen for the survey. That's selection bias. But not everyone who's chosen responds. And here's the key problem. The people who respond may be systematically different than those who don't. So what do researchers do these days? What they do is they weight the responses of those who are hardest to reach, of the demographic groups that are hardest to reach, probably the most. For example, older people, like my mom lives in a retirement community, they pretty much all answer their phone and respond to surveys. So they're overrepresented. But people, young people, rarely do. You're all on cell phones and you just don't even answer it, usually if it's a survey asking for your response. So they're doing other things too. They're doing things on, it's very difficult. What's amazing is that they are coming up with using basically, even though they're not gathering the surveys in a completely simple random way, they're able to, using the statistics that we're using, come up with very good, fairly accurate estimates. Yes? What are the characteristics are? Well, for example, let's say she wants to know what characteristics would be interesting to us up here. Well, let's say we wanted to do a political poll and we wanted to see who was most likely to win the election. Well, we certainly would want the same percent of Democrats. We'd identify Democrats and Republicans as being important, but other factors that determine whether somebody would be a Trump supporter might be hidden to us. And so if we do a random selection, those differences will average out. All right, so now let's keep going here. So basically the nice way to think about it right here is that you have this estimate right here that you get from your statistic, your sample. So this you get from the random sample statistic, and we're using it to estimate some population percentage, like the percent of voters who plan to vote for Trump. So the population parameter. But then there's bias and there's chance error. And this is reduced by random sampling, but not eliminated. And this chance error is calculated using our standard error formulas if we have random sampling. Okay, and that's what I say here. The advantage of probability, sampling is we can calculate the likely size of the chance error. So let's do that. So let's do an example. And so here we are. We're going to look at inference and confidence intervals, okay? So as I said before, thus far we've known the composition of the box and used it to draw conclusions about the composition of all possible samples. But now we're going to go in the opposite direction, which is much more common, but really harder to do. We just know the composition of one sample, and we're going to use it to estimate the composition of the population. So let's look and see how we do that. So here's a poll from last year that asked 1,002 adults nationwide. It was a random poll, I should say that. Do you or anyone in your house own a gun? And 47% said yes. I looked just last night, and it's still about the same this year. So that's what that's our sample percent right there. And we're going to use that, of course, to estimate what are all American adults who would answer yes to this question. We sampled from the whole population, so our expected value of the population percent is going to be the same. Okay, that's pretty obvious. What else would we use? But now, what's the standard error? So let's think about this. We'll set up a box model. Now remember, we don't know what's in the box. But the box always represents the entire population. It's our probability model. It always represents the whole population that we're interested in, that we're sampling from. So in this case, so this is the population, and we're interested in all US adults, so that's about there's millions of tickets, approximately 200 million tickets, right? Approximately 200 millions just millions of tickets. You don't have to know the exact amount. I'm just estimating. Basically, it's approximately that many tickets, 200 million tickets. Why? It's one for each US adult. That's what's inside this box, all right? Now, what's on those tickets? Well, we're just interested in whether they have a gun or not, whether they said yes or not. So it's just zeros and ones. So we have the ones for all the people who said yes, and we have the zeros for all the people who said no, they don't own a gun. So now we don't know these percents. That's what we're estimating from the sample. So we use the sample percent to estimate that. So that's 47%. Okay? And now what we want to do is, so we draw from this box. So our sample is, we draw, this is what we did, n equals how many? What we have to, does it say? Where's that? Here it is. So we drew 1,002 tickets. We'll say times, we drew it. Now, did we replace it? If we got a 1, do you think we threw it back in there? Are you going to sample the same person twice in a survey? No, you don't. That person goes out of the, out. It's not replaced. So we sample randomly 1,002 times without replacement. So that's different than our gambling games. And then we get, what did we get? 47% ones. All right, so that's what we use to estimate the expected value here. But now, how are we going to do the standard error? That's the problem. The standard error, the percent of ones, is the standard deviation. Here, this is the formula we're going to be using right here. But we don't know the standard deviation of the box like we did before. All right, so that's our first problem. We don't know the standard deviation of the box. Well, and the second problem is that we're drawing without replacement instead of with replacement. All right, so to deal with the first problem, what do? We use the sample SD as an estimate of the population SD. So that's what we're going to do. Okay, so remember how to calculate the sample SD. The standard deviation of a 0, 1 box, well, it's from this, or you could use this, it's just going to be the square, we just have ones and zeros, so it's the square root of 47%, 0.47, times 0.53. Okay, it's given to us by the percent of ones in the box right here. That's what we're using. And we get 0.499. And that's what we're going to use as our estimate for the standard deviation of the box. So our standard error for the percent is going to equal its SD of the box, which we don't know, over the square root of n times 100. But we're going to use that to estimate it. Okay? So what we get, if we did that, would be 0.499 over the square root of 1,002 times 100, and I got approximately 1.58%. Now the question is, all right, is that a big problem? How much accuracy is lost when we do that? We didn't make any adjustment at all. We just said 0.47, that's what we put in here. And so how much is lost? Well, you know, with the percents, very little is lost. Why? Remember we talked about 0, 1 boxes before? We talked about how the standard deviation of a 0, 1 box, always the lowest it could be a 0, and the very highest you achieve when it's 50-50, right? That's the highest. So it's always between 0 and 0.5. So it doesn't vary very much. So even if we have to draw a really strange sample, let's say the standard deviation will still be close to the standard deviation of the box. For example, let's say you have two very different samples. They're going to give you very close to the same standard deviation. So let's say one sample A has, so let's say sample A has 50% ones, and let's say sample B has 60% ones. What I'm saying is, even if you got a bizarre sample, it's still going to give you, the standard deviation doesn't vary that much in 1, 0 boxes. You can see that this is the square root of what? 0.5 times 0.5, which is the square root of 0.25. That's what we've got. And this one is the square root of 0.6 times 0.4, which is the square root of 0.24, which is equal to 0.49. So for percent problems, it's not a problem that we don't know this. This is not a problem, not knowing the standard deviation of the box. What about the second problem? We're drawing without replacement. What about the second problem? So let's look at this. So there's actually a different formula for drawing without replacement. You're supposed to multiply by this correction factor, where n's the population size. Notice in our standard error formula that never comes up because we're not sampling without replacement. It doesn't matter if you have 50% ones and 50% zeros by 500 ones and 500 zeros, or 1 1 and 1 0. It doesn't matter because you're sampling with replacement. But without replacement, you really have to adjust that formula. And this is, you're supposed to you should multiply by that factor. But if you think about it, in our example, here's our population size, here was our sample size. And if we do that, it reduces the standard error a smidgen. So most people just don't even bother with it. Okay? But let's say when the sample size is large relative to, what if you sampled the whole population? What if you took out all 200 million tickets? Well, then you would have no sampling error. You'd know exactly. You'd have everybody. So you'd have no error. So obviously, sampling without replacement reduces your standard error. But even if it's as high as 20% of the population, it's only going to reduce it. We're only going to we'll still multiply by something very close to 1, 0.9. You can see this really easily. Here, let's say our sample size is 101, all right? And let's say we have about 20% of that. So n equals about 20 there. So if we use the formula, the correction factor is equal to then what? It's our population size, 101, minus our sample size, which is what? 20, over our population size minus 1. So that would be the square root of 81 over 100, which would be 0.9. Square root of 81 is 9. So we'd still have it. What if you sampled, I don't know, like 50%? Let's say, I'm just going to do simple numbers. Let's say n was 52. Then our correction factor would be equal to what? 101 minus 52 over 100. So we'd get the square root of 49 over 100, which would be 0.7. So we'd reduce it somewhat. In other words, we're giving a conservative standard error here. And you'd have to really sample a huge fraction of the population. And this always baffles people in order for it to affect our accuracy of our sample. So this really baffles people. They always say, well, how is this possible that, a sample of 1,000 people can determine, to such a degree of accuracy, what all 200 million Americans think? And why don't we need a bigger sample for the whole U.S. than we would for the U of I, for example? Like a sample of 1,000 from the U of I would give us about as much accuracy as a sample of 1,000 from the whole U.S. if they were truly random samples. And the idea is this. Think of it as sampling as tasting. You go around, we sample things, you're tasting things. So think of sampling as tasting. You don't need to take more from a large glass than a small glass to see what a drink tastes like, as long as you mix it up. Let's say you had a glass of, mixed, let's say, I used to make these great drinks, these huge punch bowls have these great parties back when I was younger. And I put a lot of ingredients in and mixed it all up. And I always had to taste it, especially for New Year's Eve. I used to do this. And I put, a lot of alcohol in. The key was to make it not taste that way so women would drink and it would be fun. So I used to do that, and I used to take a little taste of it. But before the party, if I had to, because it was a giant one, industrial, huge punch bowl. So if I had to, as long as I mixed it well, which is like randomly sampling, just a little taste was good enough. Think about your blood. Your blood's if you go for a blood sample, you don't say, hey, I'm a big guy. I need a big blood sample. This little baby's only a little person, just needs a little sample. No, it doesn't matter the size of the person, the size of the population. It just matters the size of the little sample, as long as it's well mixed. You know that, right? Does that make sense now? Yeah, you have a question? Just going back to here? Oh, by the way, this is not going to be on the exam, not on any homework.
The last one, like on page 59, the bottom part. Like
Yeah, you can. All right, so I think that we're good on that. So now we're going to talk about confidence intervals on page 61. So let's do that. All right, so in the last example we just did, about gun ownership, do you have a gun in your house? 47% reported having a gun in the house. And standard error was estimated to be about, it was 1.58, wasn't it? Didn't we? Yeah, 1.58. So let's change that to 1.6 here. Sorry. Rounded. All right. How confident are we that our estimate's right? How sure are we that if we really polled all U.S. adults, we'd get 47% plus or minus 1.6%? That is between, just have to adjust this a little bit. Plus, it's 47 minus 1.6, 45.4 to 47 plus. What did I do here? This should be a 48.6. Sorry about these typos. Okay, saying they have a gun in the house. Now, so we can use the normal curve to answer that question because we know what? We know that the probability histogram of sums and averages and percents follow the normal curve. So what do we know? That you have some true population percent here, the true, I'll call it P. This is the true population percent in the whole population. We don't know it, right? And then once we translate it into a z-score, that would be, and the distribution of our sample percents would follow the normal curve, and it would be centered here as a z-score of 0. And it would look like this. In other words, if we did this, 68% of us would be within one standard error of the true population percent, and 95% of us would be within 2 standard errors of the true population percent, right? So that's what we know. If hundreds of pollsters, like if you were all pollsters, and you went out and you each took a sample of 1,002 people, and you asked the same question, then and you followed the procedures correctly, then 68% of you would get within one standard, would be in here, would be pretty close to the true population percent, and 95% of you would be within 2 standard errors. But even if you did everything right, if you computed a 95% confidence interval, that means that 5% of you would be out here. And when you went 2 standard errors in either direction, you would have missed the true population percentage. So we can be about 68% sure that our sample percent is within 1, right? This is the idea. We only see one sample. We don't have hundreds of people doing this. One pollster, and so one of you is doing this, so you can be 68% sure you're here, and you can be 95% sure here, but even if you do everything right, 5% of the time you're going to be outside here. So if you get, let's say, just by the luck of the draw, you got out here, or way out here, then if you went 2 standard errors over, 1, 2, in either direction, your confidence interval would not include the true population percent. So in general, the interval, your sample percent, plus or minus, what's this z star? This z star is called the critical value of z that corresponds to your confidence level. Like for 95%, that would be 2, it would be 2 standard errors. For 68, it would be 1. Okay? So let's do an example. All right. So this is the idea. This is called the critical value. So a 68% confidence interval is the sample percent plus or minus, here's the critical value. For 1 is the critical value for 68% confident. For 95%, 2 is the critical value. How about for 80% confident? How would we find that critical value? How would we find that? Well, we'd look on the normal curve. And what we want is the z-score that has, this is called z star. This is negative z star and positive. These are the critical values. that are the boundaries that have the z-scores that have 80% in the middle. So that's what we want to find out. So you would just go to the normal curve, and you'd look for 80% in the middle, and it's, for the purposes of doing it in this class, it's 1.3. I mean, if you actually looked on the computer or in a more accurate table, it's more like 1.28. But let's just say 1.3 here, unless you're told to do otherwise. So this is 1.3, and this is negative 1.3. So that's how many standard errors we attach to achieve an 80% confidence interval. What about a 90% confidence interval? Well, then we'd look at 90 right here, and we see 1.65. All right? So find a 90 and 95% confidence interval for the true population percentage. So a 90% confidence interval would be what? Would be our sample percent. So that's 47%. And how many? We're going to add and subtract a margin of error. And that margin of error is just z star, which is 1.65. That corresponds. That's the z star, the critical value of z corresponding to a middle area of 90, times the standard error. And our standard error is, in this case, I'll just write the standard error here, and it's 1.6. We got it before. So it's the sample percent plus or minus your critical value times the standard error. So in this case, what do we have? So we have 47% plus or minus 1.65 times 1.6. So another way of writing that, you'd set a lower limit of 47% minus that, which is 44.36%, all the way to an upper limit, which would be 49.64%. So you're just adding and subtracting that margin of error. All right. Let's do this one as an eye clicker. We haven't done one eye clicker. So just choose this as A, B, or C. A, B, or C. I don't even have a question for that, but let's just go over to here and just choose, what's this? Okay, just choose A, B, or C. On page 61 for part D. Okay, is everybody done with that? Can I shut it off? Okay, I'll shut it off now. And let's see what you chose. Okay, good. It's B. And let's go back to the document camera for a minute and we'll look at that. Okay, so to which population can you apply the interval? Okay, just all adults in the U.S. Why? Because you can only apply the confidence interval to the population that you drew the sample from. We couldn't apply it to the whole world, a wider population. We also couldn't apply it to a more restricted population. I'm sure that 47% of the students here don't have a gun in their dorm. So it just has to be population that you drew the sample from. Does that make sense? You can only apply the confidence interval to the population you drew the sample from. Now, let's do another clicker. I just want to make sure this is getting cemented in. So let's go to the here, and let's do the next one. Okay, so I'm going to start this, and I just want to see if you can translate it into a box model. Or no, I just want you actually, this has to do with sampling as tasting, right? You don't need a bigger population to achieve the same, a bigger sample just because your population's bigger. So I'll read this one. City A has 1 million people, City B has 9 million people. And you take a simple random sample of 1,000 people from City A, and you might think you should take 9,000 from City B, right? Because it's 9 times bigger. But other things being equal, the sample from City A is going to be what? Just choose one of these. It's kind of hard, the way I did it. This is taken from an exam. It's going to be hard for you to do right now, but just try it. Okay, I'm going to cut it off now. I'm curious what you guys did answer. Okay. I probably would have just on first glance did the same accuracy too, but that's wrong. Remember, if it was 1,000 and 1,000, it would be the same accuracy, right? You're thinking 9,000, you need more to achieve the, remember you just need the same size mouthful, whether you're sampling from, a glass or a big pitcher to taste something. It doesn't depend on the population size. So if it had been 1,000, it would be the same accuracy. But this one, remember, this million doesn't enter into our standard error formulas, the n, large N, unless we use the correction factor. So it's just, if you have 9 times as many people, your standard error is going to be divided by the square root of 9 by 3. So other things being equal, this is a smaller sample, so it's 3 times less accurate. Not 9 times less accurate, but 3 times. I didn't, that's a hard question. Okay, so let's do the next one. All right, so this is just translating into a box model. So let's say CBS asked a random sample of 1,600 adults the following question. Do you think the distribution of money and wealth in this country is fair? Or do you think it should be more evenly distributed? 26% answered fair. So what closely resembles the box model? All right, everybody has a chance to vote. So let's Stop it. And this one I hope people got right. Okay, so you knew it wasn't 2. All right, you have to look at this. This is correct. C, one out, but still there's a lot of people. I asked this deliberately because so many people get this wrong. The box is the whole population, right? So we asked a sample of we drew 1,600 people randomly from all, nationwide, right? We asked a random sample. So the box has millions of tickets because we drew the sample to estimate how many people in the whole nation feel this way. Does that make sense? So the box has millions of tickets, marked 0 and 1, but the exact percentage of each is unknown, and we're going to estimate it from our sample. Questions on that? The box represents the entire population. How did you know that here? Well, they asked 1,600 adults. They picked out of the whole nation, out of all of the U.S., all right? And we don't know what's in the population. That's why we're taking a sample. And each time we take a sample, it's going to vary. All right, so I'm glad I'm doing these because that's an important question. So let's go back to the document camera. And let's do another one that's just like that so it will help you understand. All right? Suppose a random sample of 100 female UI freshmen was taken to estimate the average weight of all, well, here I told you, all 4,000 UI female freshmen. All right? The sample average was 135, and the sample standard deviation was that. All right. Estimate the average weight of all UI freshmen. Well, that's real simple. It's just going to be the same here. But what's the standard error? So now we have to set up this box model. So what are we going to do? We have this box, and here it represents the whole population. So there's 4,000 tickets, one for every one of these female freshmen, and on each is written a weight. And we don't know what the average of the box is. The population, I'll put a Greek letter, mu for it, we do not know. And we don't know what the population standard deviation is, sigma is. We don't. But we're going to estimate it. Okay? So we're going to estimate here, and we're going to estimate with that standard deviation. That's the idea. And we're going to do that because we have our sample size is big enough. All right? So let's do it. So we set up the box model to calculate the standard error of the average. What's that going to be? Well, that's the standard deviation of the box, sigma, right? All right, standard deviation divided by the square root of n. It's of the box. That's the same thing as sigma over the square root of n. But we're going to we don't know that. And we're going to estimate it by that 25, which is 2.5 pounds. Now, we can't assume the sample standard deviation is close to the box SD like we did with 0, 1 boxes, where we know it's always between 0.5 and it's directly tied to the mean. I mean, the mean, the percent, it's directly tied to the percent. This standard deviation is not tied to the mean. There's no relation between them. The percent in the 0, 1 box is the mean, and the standard deviation is directly tied to it. That's why they're very close. It's why it's a very good estimate. This one isn't necessarily a good estimate. But when the sample size is large enough, the sample SD is a good enough estimate of the population SD for our purposes. In the next example, we're going to do something else. We're going to use a different distribution, a t distribution, and adjust this, make a different estimate. But for now, when the sample size is large, we're just going to go ahead and build a confidence interval and do everything the same way. All right? So we'll do exactly the same thing we did before. We said we can use the normal curve to build confidence intervals because of the central limit theorem. That's when n is large enough. Okay, so we can do the same thing. So this is super easy. A 68% confidence interval is just going to be our sample average plus or minus this margin of error, which is 1, that goes with the 68, times the standard error of the average. So that's 135 was our 135 plus or minus 1 times 2.5. These are all pounds. Okay? So that is equal to, another way to write it would be 132.5 all the way up to 137.5 pounds. How about a 95% confidence interval? It would be the same thing. You'd just say 135 pounds plus or minus, we're just using 2 as the critical value for 95%, times 2.5. So that would be equal to, go down 5 pounds to 130, and up 5 pounds, 130 all the way up to 140. We'd be 95% sure that the average weight was inside that range. Okay, and 68% sure that it was inside that range. Of course, the more sure you are, the more sure you want to be, you have to include a bigger range. Now, what if we had a small sample? So now we're going to look at the t distribution. All right, suppose we only had 16 females. We got the same results. Since we have a small sample and we don't know the standard deviation of the box, this 25 is not a great estimate of it. So we really should be adjusting that standard deviation and also using the t distribution. So let's look at that and then we'll do the problem. Okay, so this t distribution, so you have to refine the distribution for small n. So when we're using this small sample size, the SD to estimate the population SD is not very accurate. It's likely to be too low, so we use SD plus instead. What is SD plus? It's something you're very familiar with, I'm sure. It's when you compute the standard deviation, so you get all those deviations, you sum up the deviations, x sub I minus x bar, the average, those are the deviations, you square them, you take the average, but instead of taking the average n, you say n minus 1, and then you take the square root. So that's the SD plus. So to get from one to the other, this is the relationship. SD plus is bigger. It's also known as S. That's how you'll see it written, S. All right? Now, this is one adjustment you would make with it. You can do this with a larger sample. It just becomes very unnecessary because you can see as n becomes big, this becomes almost 1, and it's hardly any different. But, and then you use, instead of using the normal curve, we use these student t curves. Now the student t curves they're curves. It's more complicated. There's a different curve for each sample size. So here's a chart that will help you understand this. First of all, why are we doing this? We're doing this when we have to estimate a population sigma we don't know. So you're never going to use t here, never. You only use it when you don't know the standard deviation of the box. So you don't use it in percent problems because you have a very good idea of sigma just from the percent of ones you get. Your standard deviation is tied to, so you never use it for percent problems. You never use it for 0, 1 boxes. Here. That's what I say here. because you can approximate it by the sample percent with the square root of p times 1 minus p. So it's only in the situation where you have an unknown sigma. All right? Now, so this side, you don't ever use it. Now, you don't know sigma. Now, if you have a large enough sample, you can use z because of the central limit theorem. And you could use, a lot of people just use t anyway, but it hardly makes any difference. And if you have a large enough sample, you could use what allows you, you really don't need to use t, but a lot of people do anyway. You could use either one. But with a small sample, this is where you have to use t. But the t distribution depends on sampling from a population very close to normal. So so when you have small sample sizes on either side here, you have to rely, if your population is normal, you could use z here and t here. But if it's not normal, you have to use other methods that we're going to be talking about later on in the course. So that's the idea. Keep this chart in mind. And this 25 is my limit. It's arbitrary. It just basically, you have this distribution here. That's, so now you have, like, let me show you. So this tall, big one, like this one way up here is the normal. Okay? It's really small area in the tails and high up here. Now the t is the t that we can look at these t's. There's different t's, there's a whole series of them. But here's the t right here when you just have a sample size of 2. So this is the one that's going to be most different from normal. Like that. So, so basically t curves have fatter, as your sample size grows, okay, as your sample, these are the degrees of freedom. The degrees of freedom is n minus 1. They refer to just your sample size minus 1, okay? So the t curves have fatter tails. See how it's much fatter in the tail? And are flatter in the middle. See? So when we're doing confidence intervals to get that middle area 95% with the z, we can go to between 2 and negative 2. We're going to have to go further out because it's flatter in the middle to get that 95%. So our critical values of t are going to be bigger. All right, what about these degrees of freedom? What do they refer to? The degrees of freedom refer to, this comes up when we're estimating a standard deviation. We don't know it. So they refer to how many deviations go into calculating the SD when we're estimating. Since the sum of the deviations is what? The sum of the deviations equals 0. Since the sum of the deviations equals 0, once we know n minus 1 of the deviations, the last one is determined. Because they all have to sum to 0. So this degree of freedom means the term comes from the first n, the n minus 1 of them are free to vary, right? They're free to vary. But once you know those, the last one is fixed. So that's where that degrees of freedom come from. You know, if let's say all your deviations, you had 9 deviations and they're all negative 1, then you'd know your last one had to be 9 because they have to sum to 0. All right. So that's for that degree of freedom. So now we can do the problem. So we'll go back after we have all that information. And, here, one other thing I should write right up here. That we said, okay, so the standard error is equal to, for the average, we're doing these for average problems only, is equal to the SD over the square root of n. Now, what's the standard error plus for the average if we're using the t? Well, that's going to be SD plus over the square root of n, which is the same thing as SD over the square root of n minus 1. So this will make our job pretty easy now when we go back, and we'll just finish this up in just 2 minutes. So now let's do that example right here. All right, so now we want to calculate the standard error. Where are we? We're on page 62. Sorry, we're going the whole hour here, but then you'll be able to do this homework. So the SE plus is equal to SD, I'll write it again, over the square root of n. You could do it that way, or what's easier is SD over the square root of n minus 1, since we have this SD. So it's square root of n minus 1. So we have 25, and instead of saying square root of 16, we're just going to say square root of 16 minus 1. And that's the standard error plus. Okay, we've got that. Now we're going to use the t distribution to build these confidence intervals. All right, so let's do a 68, or let's do a 95% confidence interval. A 95% confidence interval is still going to be our sample percent. We're just doing it 135 still. Our sample average, 95% confidence interval for the true weight of all the girls, all the 4,000 girls. So our sample average, that's our sample average. And then what do we usually do? We're usually going to say sample average plus, we're going to have sample average plus t star, the critical value, instead of z star, times the standard error. So we don't know t star yet, but we know this standard error is 6.45. Now, to get t star for 95%, what are we going to do? We're going to have to look on the curve and get 95% in the middle. And we have to look on the t with how many degrees of freedom? The degrees of freedom is n minus 1, so it's 16 minus 1, which is 15. So we're going to look on the t curve with 6 degrees of freedom is going to be equal to 15. So let's do it, go in our bed, and then we're going to find t star right here. So it'll be t star. And we know it's going to be bigger than 2. What is it? And how are we going to find it? So let's go to our table on page 235 in the book. And here we go. And here we have the t table. And unfortunately, it doesn't do the middle area on this one. So these are the areas right here of the tail. So basically, for confidence intervals, if we're going to do confidence intervals, what do we want? We want, for the 95, we want 95% in the middle. That would be 2.5% on each tail. So that would be this one. This one would be, what would this one be? This would be a 99% confidence interval. This would be a 98% confidence interval. What would this, 5% on each tail? 90% confidence interval, 80%, etc. So now, what do we want to do? We want to look at the degrees of freedom, and we only want to look at this, 15, 95%, and there's our critical value. That's t star right there.